So, the Earth isn't just a solid rock floating around in space. It actually has these distinct internal layers. Each layer comes with its own unique characteristics, and, honestly, they play a huge part in shaping life right here on the surface. Understanding these layers well, it helps us get our heads around everything from earthquakes to volcanic eruptions. Scientists generally divide the Earth into four main layers: the crust, mantle, outer core, and inner core. These layers all vary by their composition, temperature, and even their physical state. From the thin crust to the molten core, each one plays a crucial role in Earth's systems. The crust is the outermost layer of the Earth. It's actually pretty surprising how thin it is, ranging from 5 to 70 kilometers thick, depending on where you are. The crust is where all life, oceans, and continents exist. There are two types of crust: continental crust and oceanic crust. Continental crust is thicker and made mainly of granite, while oceanic crust is thinner and denser, made mostly of basalt. These differences, they really affect tectonic activity and the geological features we see. Beneath the crust lies the mantle, which stretches down about 2,900 kilometers. The mantle is made up of silicate rocks that are rich in magnesium and iron, and even though it's solid, parts of the mantle can actually flow very slowly over long periods. The mantle is divided into the upper mantle and lower mantle. The upper mantle includes the asthenosphere, which is this semi-fluid layer that tectonic plates glide on. This flow is what drives continental drift and shapes Earth's surface over millions of years. Heat within the mantle comes from the Earth's formation, and also from radioactive decay. This heat creates convection currents that move molten rock around. Below the mantle is the outer core, a liquid layer mostly made of iron and nickel. It extends from about 2,900 to 5,100 kilometers beneath the surface. The outer core's swirling molten metal is what generates Earth's magnetic field. The Earth's magnetic field protects life by deflecting harmful solar radiation. Without the outer core's movement, this protective shield just wouldn't exist. It's an invisible force, but it's got life-sustaining importance. The innermost layer is the inner core, a solid sphere about 1,220 kilometers in radius. Even though the temperatures are estimated around 5,400 degrees Celsius, the immense pressure keeps it solid. The inner core is mostly made up of iron and nickel. Scientists believe the inner core actually rotates at a slightly different speed than the Earth's surface. This was discovered using seismic wave data from earthquakes, which is pretty wild if you think about it. The boundary between the crust and mantle is called the Mohorovičić discontinuity, or just the MOHO for short. It marks a sudden change in rock density and seismic wave speed. This boundary was first identified back in 1909 by seismologist Andrea Mohorovičić. The mantle's uppermost part and the crust together form what's called the lithosphere. The lithosphere is broken into tectonic plates that are constantly moving and interacting. These movements cause earthquakes, mountain building, and the formation of ocean trenches. The boundary between the mantle and the outer core is known as the Gutenberg discontinuity. It's identified through the behavior of seismic waves, which change drastically at this depth. This really helps scientists map out Earth's inner structure. Seismic waves provide most of what we know about Earth's layers. By analyzing how these waves travel through the planet, scientists can, infer the composition and behavior of each layer. This method is kind of like using sonar to explore unseen worlds. Earth's layers were formed during its early history through a process called planetary differentiation. Heavy elements like iron sank to the center, while lighter materials floated toward the surface. This process created the layered structure we study today. The heat and pressure increase dramatically as one travels deeper into the Earth. For every kilometer of depth, temperature rises by approximately 25 to 30 degrees Celsius. This extreme environment is way beyond the reach of conventional drilling. The deepest humans have drilled is the Kola super deep borehole in Russia, reaching about 12.3 kilometers. Despite being impressive, it barely scratches the surface relative to Earth's total depth. The Earth's layers remain mostly unexplored directly. Volcanoes provide natural insights into the Earth's interior. Magma from the mantle reaches the surface, carrying minerals and elements from deep within. Studying volcanic rocks helps geologists understand the composition of the mantle. Earth's layered structure is critical for plate tectonics, which shapes continents and oceans. Without these internal movements, Earth would be a static, lifeless planet. The dynamic Earth is constantly changing beneath our feet. Earth's layers also affect natural resources. Many metals and minerals essential to modern technology come from specific layers. Understanding geology helps industries locate and responsibly extract these materials. Earth's magnetic field, generated by the outer core, creates the beautiful auroras near the poles. These natural light shows are visible reminders of deep Earth processes. Without the core's activity, auroras would not exist. The study of Earth's layers is called geophysics. This field combines physics, geology, and engineering to uncover the planet's mysteries. Geophysicists use cutting-edge tools and techniques to build more accurate models of Earth's interior. Understanding Earth's layers helps us comprehend natural disasters like earthquakes and tsunamis. Preparedness depends on predicting how and where these events will occur. Science continues to improve early warning systems. The layered Earth is a marvel of nature, hidden beneath our feet yet affecting every aspect of life above. From the solid crust we walk on to the swirling outer core deep below, each layer plays a vital role. Exploring these layers connects human curiosity with the grand scale of planetary science.